Several sections ago, we looked at how to take the orthogonal projection of one vector onto another vector. And so just to remind you of that, say we have some vector x, and we're finding the projection of x onto some other vector. Okay? So graphically, what the orthogonal projection looks like, we drop a perpendicular from vector x to vector f. And the orthogonal projection of x is the amount that x travels, but just in the direction of f. So we have the projection of vector x onto vector f, and the formula for that is the projection of vector x onto vector f, which is the dot product of x and f over the norm of f squared. And that's the scalar multiple of vector f. All right, so this should look familiar because, of course, we have done orthogonal projection before, but also we just saw this when we were looking at how to represent a vector x as a linear combination within a subspace within orthogonal basis. We could express x as a linear combination of those orthogonal vectors, where the terms of that linear combination look just like this, right? So we're going to expand on this idea. Instead of projecting x onto just a single vector, what if we project x onto a subspace? Okay, so what would that look like? Let's say we have some two-dimensional subspace, which means a two-dimensional subspace is a plane, right? So we have some two-dimensional subspace. All right. And we want to project vector x onto this two-dimensional subspace. So this is kind of what we're looking for here. So we're going to call this subspace W. And we want the projection of x onto subspace W. Now, it turns out this is actually very straightforward to do, so long as you have an orthogonal basis for subspace W. So let's say we have some orthogonal basis. Let's say we have F1 and F2. I'm going to say F1 and F2 is an orthogonal basis of vector space W. All right. So the trick here is that because the two vectors are orthogonal, all we need to do is we need to find out how much of x is going in the direction of f1, how much of x is going in the direction of f2, and then if we add those together, we get the full projection onto vector space W. All right? So we want how much of vector x is being projected onto vector f1. And how much is being projected onto vector F2. We have the projection of x onto F1. We have the projection here of x onto F2. Okay. Notice that if we add this projection together with that projection, it would give us the full projection onto the vector space. I hope that kind of makes sense, that you kind of see that. Okay. It only works because we are dealing with an orthogonal basis for vector space W. And that way the projection of x onto each vector in the orthogonal basis, it is describing the direction of x in totally different directions. Okay, how much of x is moving in that subspace, but in different directions in that subspace. There's no overlap, so there's no overcounting, there's no undercounting. Okay, so hopefully that kind of makes sense, but if not, the formula is pretty straightforward to follow. Okay, we have the projection of a vector onto a subspace of Rn. So let's let W be a subspace of Rn with an orthogonal basis F1 to Fm. If x is a vector in Rn, any vector could be in the subspace W, but it doesn't have to be, then the projection of vector x onto subspace W, we'll call it vector W, is just going to be the sum of the projections of x onto each vector in the orthogonal basis. We call this the orthogonal projection of x onto the subspace W. Okay, so you just need to take the orthogonal projection of x onto each vector in your orthogonal basis, then add it together. That will give you the projection of x onto subspace W. It will tell you the portion of x that's traveling within that vector space.